which is called triple integrals. And really properly, it should be called triple integrals in Cartesian coordinates. Because the next two chapters are going to cover cylindrical and spherical coordinates. So the basic idea here is, if I'm sort of working by analogy, when I set up a notion of integrating over a domain in R, one variable integral or single integral, what I did was I took my interval a to b and I cut it up into little bits and I called that dx, right? And that led to an integral in terms of delta x. When I was working in R2, I have some domain d, and the way that I built an integral in this context was I cut this thing up with sort of a Riemann sum setup, and then I identify these little rectangles that I'm approximating over, and those guys were called dA, right? So dA, and then we observed, I should call it delta A, that delta A was delta x times delta y, and that gave us a notion of double integrals based on cutting the domain up into these little areas. If I'm in 3D, so here we have y as a function of x, here we have z as a function of x and y. In 3D, the domain of my function now is like a solid region floating in space. So we can think about it as being some sort of blob. We can think of it as being a cube. And our functions eat things in 3 variables and then produce an output. And the basic idea here is, instead of decomposing it into little squares, because I'm working essentially with an object in 3 dimensions, I'm going to decompose it into little unit volumes instead. So living inside this is a whole collection of little tiny cubes that make it up. And these we call dV. And it shouldn't be hard to believe that if you have a little tiny unit of volume, you can approximate it with delta x, delta y, delta z. So our notion of a triple integral basically is this. We're going to say, this is our definition, the triple integral of f over, say, a box in R3. So this picture where you have a box is going to be the triple integral over b of f of x, y, z, dv is, and I'm only going to write this once and we're not going to use it, but at least I want to show you the Riemann sum version of this. The limit as L, m, and n go to infinity of the sum where I goes from 1 to L, j goes from 1 to m, k goes from 1 to n, of f of x I j k, y I j k, z I j k, some number chosen from the center of the box to evaluate the function at, times delta x, delta y, delta z. It's literally the same definition we've used 3 different times now to build this up. Now it's weirder to interpret what this means, of course, because I guess this is like the volume of a 4-dimensional rectangular parallelepiped where the base of the cylinder is this cube and the height of it is this other 4th dimension. So it's hard to physically make this make sense in a way that corresponds with our way of thinking of double integrals as representing volumes. There's some 4-dimensional quantity that this is measuring. It's hard to intuit what that means. So instead what we do is I'm going to show you some typical applications of this idea instead. And then when we get into the integrating over scalar fields part of the class, it'll be much easier to make physically meaningful how you might interpret something like this. Okay, so here's some typical uses of these types of integrals. One thing to observe would be, that's going to justify the first observation is, if I have some domain D contained in R2, and I just double integrate the function 1 dA over that region, what comes out when I do that? What if I just don't even put a function, I just do the integral? The integral of d dA, all by itself. What should come out?
The area?
Yeah, it's the area of the domain. The one way to think about that is, this would be like integrating the volume of a cylinder that had the base area of the domain and height everywhere equal to 1. So the volume and the area would be the same thing, because area times 1 is equal to the volume, right? This is a mathematician way of doing it, where the units you just toss. But this is the area of D. If you want to compare this in the one variable case, that's the same thing as saying, what is the integral from a to b dx? There's no function there, it's just 1. If you do this integral, you get b minus a, which is the length of AB. So what should this be? What if I did a triple integral over some region in space, E dV? Volume. Okay, so these are some sort of typical things that show up when you start doing this. The other application that we've seen before for triple integrals, and I will promise you that I'm not going to make you do this, and we can think about why in a second. Actually, I should say, I promise you I won't make you do this on an exam, is center of mass in 3D takes the following form. Given a region E and a density function rho of x, y, and z, the mass is equal to the triple integral over E of rho of x, y, z dV. So you can imagine if I concretely ask you to do that, there's 3 integrals for you to do for the price of 1. And if you want to compute the center of mass now, x bar is going to be equal to 1 over m of the triple integral over E of x rho of x, y, z dV. Y bar will be equal to 1 over m times the triple integral over E of y rho of x, y, z dV. Just appreciate how many integrals this is going to be. Z bar is 1 over m times the triple integral over E of z rho of x, y, z dV. So if I gave you a question like this in a test, you literally got 12 integrals to do. And that doesn't, to my mind, that doesn't measure anything, right? Like what you can do or can't do on a test. If you can do 1 integral, you can do 12 of them, right? But this is one of the reason that we talk about this is because this is one of the natural motivations for even wanting to study triple integrals in the first place, is to give us a natural way to extend to a higher dimension ideas that we already have in 1 and 2. That's typical of these kind of things. So I guess the first thing I'll do is an easy example of computation. We'll work our way through a computation. You will observe that the computation is pretty easy, and then we'll talk about which problems are hard and why. We'll do some examples of some harder questions. So we will start with this problem. The integral from 0 to 1 of the integral from 0 to z of the integral from 0 to y of z e to the minus y squared dx, dy, dz. It is very important, especially when we're working with triple integrals, that I pay attention to the order that is imposed by this bit right here. However I've chosen to express dA. So, working from the inside to the outside, just like in double integrals, we're going to solve this integral first. Most people got this figured out by the time of the exam, but remember, if I'm integrating with respect to x, and that thing inside there has no x inside of it, it's constant. Integral from 0 to 1 and 0 to z of z e to the minus y squared x evaluated from x is equal to 0 to x is equal to y. It is not strictly necessary to say that you're plugging things into x this way, but when there's enough variables running around, it's not a bad idea to just do some bookkeeping. Evaluating that, you get, let's see, z e to the minus y squared y minus 0 dy dz. Now we move on to the next one. Okay, so the antiderivative of y e to the minus y squared is minus 1/2 e to the y squared, e to the minus y squared. So this is the integral from 0 to 1 of z times e, there's a minus 1/2 of e to the minus y squared, evaluated from y is equal to 0 to y is equal to z. You could use u substitution here, I just did it directly. A note of caution, when you're putting zeros into exponentials, remember e to the 0 is not 0. So this gets you the integral from 0 to 1 of them. Now you should double check me to make sure I'm doing this correctly. There's going to be a z, because that didn't get plugged into a minus 1/2 e to the minus z squared. And if I put in the 0, I'm going to get a plus 1/2. I believe. So this is 1/4 of e to the minus z squared plus 1/4 of a z squared evaluated from 0 to 1, which is 1/4 e to the minus 1 plus 1/4 minus 1/4 minus 0, which is 1/4e, I think. So what I want you to observe about this process is that the way that we stack the variables up is important. I could have had this thing, this first step here, when I integrated the x's away, this step could have been a function of y and z, and that would have been fine. The x step got rid of any x's in the equation. When I integrated with respect to y, I got rid of all the y's that were left. And finally, when I'm finished, when I integrate with respect to z, it better be the case that I'm integrating with respect to numbers, or there'll be variables left over when I'm finished. The order of integration sets up what can be functions of what when we set up our limits of integration. And that is the hardest thing about doing this. So when I look at that region right there, you might think, well, you could have set this up so that we couldn't have started. If you started with a dy integral instead of a dx integral, I could not have integrated e to the minus y squared, and maybe we would have to change the order of integration. That is a significantly more complicated thing in 3 variables than 2. So I'm going to do an example now of what the actual hard problems are. This is not hard. 3 standard integrals in a row it's annoying, and it's easy to make small mistakes along the way, but nothing we did here involved any technique more than u substitution. If instead I gave you a more typical question, like an exam level question even, so not even that hard, I could say something like, find 2 different integrals expressing, or to calculate, the triple integral over e of a function f of x, y, z dv. So I'm not even giving you a function. I don't want you to integrate. I just want you to set the integral up, where e is the tetrahedron that passes through this point right here, which is 2, 0, 0, this point, which is 0, 1, 0, and this point, which is 0, 0, 1. If I wanted to write this in terms of equations, what I would say, the region bounded by x equals 0, y equals 0, z is equal to 0, and I think the equation for this plane is 1/2 x plus y plus z is equal to 1. Okay, so I've given you a region now. Pretty easy one. It's just lines and planes. And the idea is, from this tetrahedron, I want to build limits of integration. So the way to think about the approach to these questions is, the first thing that we need to do is we need to identify a floor, some sort of floor for our region that we're traveling between two things, a floor and a ceiling. I have to get from the floor to the ceiling. And it has to have straight up and down walls. Like in this room, for example, I could choose the floor to be the floor and then think about the z variable as traveling from the floor to the ceiling, and then that gives me relations on the x and the y that say where the ceiling actually sits above. So pick. One of these planes we can just choose to be the floor of the region. What do you choose? XY plane. That's a pretty good way to start. So let's think about this region down here on the bottom as being the floor for now. And from that we'll try to derive some limits of integration. Essentially, so the first thing I'm going to do is I'm going to draw that floor. So that floor sits in the xy plane. X is at the point 2 and y is at 1, and so we're looking at a triangle that looks like this. If I draw this in the xy plane, that's what I've just captured. And what I'm going to say is, okay, at any point inside the xy plane, so for any x and y, I need to figure out where the z values travel. If I'm sitting at this point in the plane, I'm going to start at the bottom, and I'm going to travel up through the solid until I hit that tipped down plane, right? That's going to be the ceiling, is the angled part sitting on top. So for a particular value of x and y, what values do the z's travel between? The z values travel from the floor to the ceiling of the region that we're working on, or bottom to top, however you want to say it. The floor is pretty easy, 0. How do I characterize where that hits the ceiling?
Do you just transform that until it's a function?
I need to have z as a function of x and y, right? For a given x and y, I need to be able to tell you the z values that go along with those x's and y's, which means I need to translate the equation of this plane into z is equal to 1 minus 1/2 x minus y. From the floor, z equals 0, to the ceiling, which is the plane, 1 minus 1/2 x minus y. Great. If you told me the x and y, I can tell you precisely the z values that we travel between. Of course, now I have to choose to either fix x and figure out the y values that they travel between, or the y and tell you the x values they travel between. Now I've got a double integral problem. How do I characterize this region by inequalities? Probably I want to start by writing the equation of that line right there. I think this is y is equal to minus 1/2 x plus 1. So for a fixed value of x, the y values travel between 0 and minus 1/2 x plus 1. And finally, I just need to know where the x's are. 0 to 2. So there's a hierarchy of dependence here. Z can depend on x and y because you're saying for a given position in the floor, what are the ceiling values and floor values? This says, okay, well now you're just living inside the floor, so y can depend on x, and x can't depend on anything. It has to be a constant. When you set this integral up, you're going to integrate dz, which will get rid of the z's, and then dy, which will get rid of all the y's, and then finally dx, which will get rid of everything that's left, which will be x's. This particular set of inequalities says that this integral could have been expressed. So one way to express this integral would have been the integral from 0 to 2 of the integral from 0 to minus 1/2 x plus 1 of the integral from 0 to 1 minus 1/2 x minus y of f of x, y, z integrating dz, dy, dx. Getting rid of the z's would stick a bunch of x's and y's in its place. Getting rid of the y's would kill all the y's and replace them with x's. And finally, integrating with respect to x should just give you a number. But I told you need to do this 2 ways. So now we better choose a different floor. So now somebody says, do it a different way. So there's 2, there's 1, and there's 1. There's your tetrahedron. Pick any of the other planes to work with.
XZ.
XZ. Okay, so now, if this is x, and this is y, and this is z, this now is going to be the sort of base of our figure. Yep.
Can we still use the XY plane and then go over X first and then Y?
What do you mean?
For our second integral, instead of doing it with respect to Y, do it with respect to X.
No, because I've actually changed. You mean for this setup right here?
If we were back to the previous floor.
Oh yeah. In the previous floor, that is another way to set this up. It's absolutely right. You could have actually written this instead. If you'd in the second step, if you'd chosen the same floor but switched the relationship between x and y, yeah, I should have pointed that out. That this is y is equal to minus 1/2 x plus 1. But doesn't that also say that x is equal to 2 minus 2y? I think. And so that means that you could have also written this as the integral from 0 to 1 of the integral from 0 to 2 minus 2y of the integral from 0 to 1 minus 1/2 x minus y of f. D, now not dz dy dx, but dz dx dy. Yeah, you could instead of saying pick x and figure out the y values that travel between, you could have also picked a y and figured out the x values that it traverses instead. And often, so this is basically everything we learned about double integrals is at play here when we're doing a 2D region like this. Okay. The other possibility is maybe you pick a different base because for this particular function, this is the natural way to think about the bottom of the figure. And I guess in that case, you would be writing, here is your xz plane, this is 2, this is 1. I guess you're going to get exactly the same sort of setup because of the symmetry that I've built into this problem. So in the xz plane, this line would be the line z is equal to minus 1/2 x plus 1. Your ceiling and floor now, you are picking a value in here, which is an xz value. So I'm doing all this because I'm trying to keep straight three-dimensionally what it is that I'm doing. I'm picking a point in the xz plane, and I'm traveling from that floor up to the surface. So the y's are what's moving this time, because I'm going from the floor to the ceiling, thinking about it. This is the sort of height direction. So my y values are going to go between 0 and now have I erased the equation of the plane? So the plane was 1/2 x plus y plus z is equal to 1. So if you solve that for y instead, you get 1 minus 1/2 x minus z. Given an x and z, I can tell you where you land on the plane. And then you can do exactly the same thing we did over there. If for a fixed value of x, the z values travel between 0 and minus 1/2 x plus 1. The x values that we need to consider are x's between 0 and 2. So another way of writing that integral down, because what we need is lots of different ways of doing it, is the integral from 0 to 2 of the integral from 0 to minus 1/2 x plus 1 of the integral from 0 to 1 minus 1/2 x minus z of f, z dy dz dx. This is the hard part of doing this. Characterizing the region in terms of inequalities and then writing down the integral, this is the hard step. So often exam questions say, write down an integral that calculates this, find a triple integral that calculates this volume. Or calculate a triple integral that calculates this particular integral. This is the hard part. So let me give you a slightly more complicated question. So these are pretty easy when we're talking about planes. So I'm going to give you something with slightly more sophistication this time. Oh, I guess the other thing to point out is it would be obnoxious of me to give you a bunch of these where you have to compute a bunch of triple integrals because I already know you know how to do integrals. The setup is more important than the execution on exams. On the homework, you should practice carrying through the integrals. On exams, you will not be asked to compute horrendous triple integrals. I promise. Okay, so now I'm going to say write an iterated integral to calculate the triple integral over e of x plus 2y dv, where e is the region bounded by x is equal to y, x is equal to z, z is equal to 0, and y is equal to x squared. Those are all surfaces. The first thing to think here. Those are surfaces, which means that's all in 3D. All of those things are in 3D. I've got a plane in a different direction, a plane in a different direction, and then a parabolic cylinder. Y equals x squared, but forever in the z direction. I don't even know how to pick the ceiling for this thing, or the floor. I have no idea how to begin. I have to be able to choose a bottom for this thing. So when you're on your homework, you want to develop some intuition for this. I'm going to turn that on. You want to develop some intuition for this. You can draw these things. So let's see. I want this one. No. Let's see if I can get this to load up here. This dude. Okay. So this is in Math 3D where I've just put in the three figures. So x is equal to y. I can just turn them on one at a time. X is equal to y is blue. X is equal to z is the red curve. And so you should already see here that we've got this intersection of two planes happening. If I turn on z equals 0, that tells me, okay, well, there's the floor of what I'm looking at. So now three planes intersecting. And if I add in the cylinder... Oh, there we go. Okay, so this figure that I've got right here, I'm going to spin it around a couple of times so you can see it. You can imagine that if you took that shape between the parabola, the green curve, and the blue curve right there, that the orange curve that cuts through it, I mean, you can look at this and say, all right, what should I choose for my sort of natural ceiling and natural floor for this figure? I need the walls to be straight up and down, and I need to travel between something on bottom and something on top. So what plane should I choose here to be my basic sort of setup for the bottom of this figure? I would probably pick z equals 0 as the bottom, right? So from my visualization, I look at this and I think, all right, so z equals 0, which is the horrendously colored brown plane here at the bottom, that very much looks like the bottom of the figure, right? And then the figure is kind of this parabolic thing that comes up out of that plane. So if we picked z is equal to 0, then the bottom of what we're looking at, okay, so let's go back to the flat plane and see from the top, it looks like what I'm looking at is, I'm looking at the region between the curve y equals x squared and the curve y equals x. So in the xy plane, I have a blue curve that looks like this, which is y equals x. And I have a green curve that looks like this, which is y is equal to x squared. And the figure sits over the top of that bottom. Over the top of that bottom is a really elegant way to put that, yeah. This is the floor for the figure that we're looking at. And then coming out of it at you is the plane that's coming up like this, right? So that plane, the orange plane that's coming up, is dictating that we travel from that base up to some position in the plane. So this guy is the position xy. And for that particular value of x and y, we think, okay, well, where do we travel between? If I'm inside this little room right here, and the floor is down here and the ceiling is up here, then I know that I'm traveling for z values between what and what? 0 and z is equal to x. The orange plane is the z is equal to x plane. How about the y values? Actually, now you can choose. You can pick now. You can pick to fix y and figure out where the x's are traveling, or fix x and figure out where the y's are traveling. If you hate square roots, I suggest that you fix y and fix x and then figure out where the y values go. For a fixed value of x, the y values go between x squared and x. Being very careful to make sure we go from bottom to top. And then where do the x values live? The x values go from 0 to 1. So this particular problem, if we visualized it correctly, the solution to this would be the integral from 0 to 1 of the integral from x squared to x of the integral from 0 to x of x plus 2y. And then we're not going to use dv because I've got to tell you what order to do this in. First we do dz, then we do dy, then we do dx. So generally when we do these problems, you want sort of a top-level view of how to do this. The general approach boils down to step 1 is you have to choose a floor, which would be one of the planes, xy, xz, or yz. So, for example, we could have picked the xz plane. 2, then you stack your inequalities. In the case where you've chosen the xz plane to be your floor, it will be something like y has to be trapped between functions of x and z. So g2 of x and z and g1 of x and z. And then one of the variables has to be stuck between the others. So maybe we have x stuck between an h1 of z, h2 of z, and an h1 of z. And then z has to be stuck between two constants. So you have to have 2 variable dependence, at most 2 variable dependence, at most 1 variable dependence, and then constants. Generally, that's what every one of these exercises is going to look like for anything we can actually do this translation from a region into a problem we can integrate. Okay, next question. Could I have done this a different way in this case? In the setup that we've got here, could I have chosen a different part of the figure to be the floor? And that answer will always be yes, if you can figure out a way to make sure that that region has straight walls. And it doesn't look like it does in this case, right? If we try to say that we want the blue curve to be the base, it doesn't look like... Is that actually, do you see how the blue plane and the orange plane are not perpendicular to each other? That's like saying I've got a floor, but one of the walls sticks out like this. So it's not the roof of the room isn't consistent, right? I've got this extra bit hanging out the side in that case. You need it to be the case that when you've chosen a floor, that you've got this sort of cylindrical setup. You're over a base, the region that you're sitting over the top of forms a cylinder that's cut off by some sort of surface that forms the top of it. So when you're doing these exercises, I think in the homework it says something like, hey, here's the ones I want you to know, like, 1 through 12 or know how to do. It's just this exercise. Draw a region, figure out the inequalities, set up the integrals. That's what I'm after with this. The integrals are less important than the setup. Do I have another one of those for you to think about here? Not that. That's terrible. Okay. So here's about the most... Should I give you that to do yet? I should save that. is 5 minutes. Okay. Here is the most annoying exercise you could possibly be given in this, by far. The integral from 0 to 1 of the integral from 0 to 1 minus x squared of the integral from 0 to 1 minus x of f dy dz dx. Here's a traditional exercise. Write that in every other possible order. Don't do the integral. Just set it up 6 times. It's tradition. It's like you're being inducted into the cult of people that do triple integrals. So the first thing you've got to do is figure out, what am I even looking at? What is the region that I'm being asked to consider here? To which my response would be, maybe we should put this into Desmos or Math3D and look at what the region looks like. Because I can read off the inequalities from here. I know that I am stuck between y is 0 and y is 1 minus x. And that z is between z is equal to 0 and z is equal to 1 minus x squared. And x is stuck between 0 and 1. So I can just read off the inequalities that bound the region. I actually don't know what this looks like, so let's go look at it. Okay, what are we doing here? Y is equal to 1 minus x. And z, I'll put a z here, and a 1 minus x squared there. And then x is equal to 1. Oh yeah, I don't even know what the regions are that we're looking at here. Like these graphs. Okay, so is it this little room contained inside right here? Is that what we're doing? So we go from z equals 0 to z is equal to 1 minus x squared. So that's from the floor up to this green part, the green roof there. And then we are between x goes from 0 to 1. What have I missed? Oh, this 1 minus x thing. And y goes, yeah, I think that's right. I think it's this little room right there. Do we even have a prayer of writing that thing down with respect to 3 different bases? Like if I think, okay, if I want this side right here, this box, actually I should probably draw this one. So let's see. So it's like this, and that comes across, and then down, and then this sort of curls down into a parabola, and then there's this triangular side that comes across the back, and then there's a curve that comes down like this. I think this is, it's like take a soccer goal and shave it, like just run a 45-degree angle from this post back to the back post, right, as the figure you get out the other side. So when I look at that, I think, is it even possible for me to set this up with respect with 3 different integrals? I think the answer is probably yes, because notice that the walls, if I chose that to be the base, I have a consistent floor and ceiling, and everything else is straight up and down. Straight lines that dictate. It sits over a triangle. If it sits over a triangle, I can do it. I could have chosen this side to be the base if I wanted to. And then I'm going from this base down here. This is consistently underneath the curve. That's the green curve right here. It's like I've chosen this to be the base, this part right here. Notice that that's straight wall. They're perpendicular to the flat surface here. So I could set it up with respect to that base as well. And then the third possibility is this one as the third base to choose. That's like this rectangle right here. And now the roof will still be the green curve. Except there's this weird curve that cuts through it where part of the roof looks like, you see where the complication is going to be. If I take that to be the floor, I have 2 different roofs I need to deal with. One of the roofs is the blue curve and one of them is the green. That would not be a pleasing direction to compute this integral with respect to. Whereas if I turned it this way, you can see that the roof is just the blue curve. Just it's up to perspective is the reason why it doesn't look like it. And if you do it, what direction did I miss here? That curve, oh, this way. And then you can't even see. It's like, I'll do it that way. The green curve is consistently the roof in that case. So this stuff takes practice to visualize. It takes practice to draw these things. It takes practice to translate what you're looking at into plane pictures to figure it out. Take the time to do that. The visualization that we're doing here and the translation is more important for everything we're doing going forward than the actual computation of the integrals. Okay? All right. That's enough for today. See you guys.